Okay. Hello everyone. Today we're going to be talking more about dynamic programming, talking a little bit about how we might optimize our dynamic programming states, but also how we might have some more complicated states to be able to represent more types of problems. So, first, I'm going to be talking about how we can maybe optimize dynamic programming using data structures, which is our favorite topic. So, for example, consider the following problem. You have a permutation P of like the first n integers, and what you want to do is you want to find the longest increasing subsequence. So, for example, over here in this example array, you see that the longest increasing subsequence is the longest subsequence we can get from this array such that it is always increasing. So in this case, you would pick the 1, the 3, the 6, the 7, and the 8, and this would give you a longest increasing subsequence of length 5. So how might we go about approaching this problem? Does anyone have any basic, I guess, n squared DP ideas for how you might approach this? Yeah?
DPI of j is the longest increasing subsequence when you consider the first I numbers, and the largest number you can choose from is j.
Yeah, this is essentially what we're doing, except we're doing it like slightly different so that it's easier to transition. And the idea is that it makes it a lot easier to transition when we have to take the last element, right? So let's say that dpi is just the longest increasing sequence over p0 to over the first I numbers, basically, such that we have to take the last element. So the reason we do this is think about the transitions, right? All we need to do is figure out what the second to last element was, and so now we can just tack on I to the end of it, and now we know that this is our transition. So, for example, how might our transition look? So, we would iterate over all possible j, such that j is less than I, and it can possibly be the second to last element. But when can j be the second to last element? Well, it can only be the second to last element when p of j is less than p of I. Or in other words, only when the second to last element is less than the last element, because it has to be increasing, right? So I guess as a demonstration, we can try running our DP over this array. So for example, when we go on the first number, 9 is the only DP state. So the maximum would be null, or in this case, we would set, if there's nothing to maximum over, then we would set the maximum to be 0. And so our DP would be 1, which is reflected in the table. So does anyone want to fill in the next entry of this DP? So what might DP of 1 be, where you want the first two elements and you want the LIS over that over the last element? What would this be? Yeah?
It would just be 1.
Yeah, this would also be 1. Because again, there's nothing to max over, so when there's nothing to max over, we set the max to be 0, and so we output 1. Does anyone want to do this one? What might be the next element of our DP array? Anyone? Yeah, again. 2, yeah. And the reason it's 2 is because here 1 is less than 5, and so that means that we can take the max over something, which is DP of 1, which gives us 2. And so here we can see that we're taking the max at that position, and we're getting 2. Does anyone else want to try the next one? Anyone? Yeah, it would be 2 again, and for the same reason, because we're maxing over the same set of elements. And so the next one, does anyone want to do it? Yeah? Yeah, it would be 3, because now we're maxing over more elements, and in this case the max would be the element under 3. And so we can keep going, and once we keep going, we'll eventually generate the entire DP array. And at the end, the answer that we want is just the maximum among all of these. Because remember, our DP forces us to take the last element, and so to get the answer, we need to max over all of the possible DP states to be able to get the answer, which in this case would be 5. So, does anyone want to know what the time complexity of this is? Or want to guess what the time complexity is? Yeah?
N squared.
Yeah, this is n squared. And the reason it's n squared is because we have n states, right? We have dp 1 to ... up to n, and our complexity overall is n squared. So how might we be able to optimize this? Well, for one, we can notice that every time we're querying or every time we want to do this operation over here, which is like take the max along everything that's less than it, it feels kind of like a range query, where we're trying to find the max over a range, but also with this extra condition that p of j is less than p of I. And what this inspires us to do is this makes us want to use a data structure, a range query data structure, like a segment tree, to be able to solve this. And the way we might be able to approach this is, suppose we instead kept a segment tree where dp is indexed by p of I. So in this case, we would have like, our segment tree, and it would be indexed from like 1, 2, 3, 4, ... up to like 9 in this example, right? So what happens is every time we update a number, let's say, for example, we go back to our previous example and we say, okay, so we found dp of 1, well, we store it at 9 because that's our p-value at that point. And so we store the dp value of 1 over here, and then for 1, we store the dp value of 1 here, and then for when we calculate 5, we store the dp value of 5 over here. And so in the end, what we need to do is we need to essentially, like, for example, if we wanted to query, let's say we're at 3 and we wanted to query, what would the dp value here be? Well, the dp value here would just be the maximum over all the dp values here. And the maximum over this range is 1, so the dp value is 2. So how this might look in code is every time we query to find the dp value, we query what the answer in this range is. So for example, from 1 to 2, we query this value, and we find that our dp value is 2. And then after that, we need to update within our segment tree that the dp value at this index 3 is equal to 2. So here, me setting this value to 2 is essentially that update operation of changing this to 2. And again, at the end, to find the answer, all we need to do is to find the maximum over all dp values, because again, dpi forces the last element to be taken, so we need to max over all possible dp values. Does this make sense to everyone? Okay. So this is one way we can approach doing longest increasing subsequence. But there are actually other ways, and we don't actually need a segment tree to be able to do this. So I'll present an alternative method that we might be able to achieve the same complexity of O of n log n, where we don't need to use range queries. And so in this alternative solution, let's reframe our DP states. So we had quite a bit of freedom to frame our DP states before, and our choice of like dp of I, where we force the last element to be taken, is a pretty natural one. But in this case, let's try to do a different kind of DP. So let's say our DP stores again, we're operating over a prefix of the permutation so that we get nice subproblems. But now, let's say that we have an increasing sequence of size j, and we want to find the minimum possible last element within this permutation. And again, we're phrasing this in a pretty interesting way, And the reason we frame this, again, is so that it makes our transitions slightly easier. So in the table over here, you see that every single time what's going on is we can continuously keep this DP array, and it's very easy to figure out, for example, from DP of 1, which is on the very left, we see that like the size 1 is 9, and everything else is undefined, or in this case, we could consider it infinite, right? And then on the next side, on the next one, all we need to do is go through this array in increasing order and just figure out, can we add this element to the end of that array, and would that end up being better? And so I guess let's work through the transitions together. So there are a few cases, but let's try to work them out one by one. So let's say that in our previous array, let's say our previous array looked like 1, 2, 5, 7, and then like everything afterwards is infinity, right? And now our next element is 3. Well, so let's say we wanted to find this new array, okay? So if dp of I minus 1 of j, which is size 1, right? If our size 1 LIS already has something that is smaller than p of I, in this case, which is 3, what must this be? Anyone? Well, if we already have something better than what we can make, right? We can just keep our previous thing because it's better than what we can make in our new DP array. So we keep this 1, right? And so again, for 2, what are we going to do here?
Wait,
yeah?
can you clarify what's the original array again?
So let's say our DP array looks like this. Maybe our original array may have looked like 1, 2, 5, 7, 3, and we're trying to insert 3 into this DP.
Is it 9, 1, 2, 7, 1, 2?
Oh, the original example was 9, 1, 5, 3, 6, 7, 2, 4, 8. Yeah. Okay, so let's say we wanted to figure out what is the best LIS I can make with size 2. Then what would it be? So either we have two options, right? We can either tack 3 onto the LIS of size 1, or I guess we can tack 3 to the increasing sequence of size 1, or we can just take the increasing sequence of size 2 that we have already, right? And so because 2 is better than 3, then we take 2. And similarly, we can do the same thing. We can tack 3 onto the LIS here, or we can just take this. So in this case, we would just take 3. And similarly, we can try to tack 3 onto the end of this LIS, or we could just take what we have already. But what happens if we tack 3 onto the end of this LIS? Yeah?
What are the vertical numbers?
So the vertical numbers is like, this is like a size 1, this is a size 2, and then these are the last elements of that like increasing sequence.
Where are you in the array now?
Wait, so imagine your array was like, imagine your array was like 1, 2, 5, 7, 3. Then you already have the DP values calculated for these, let's say, and they're 1, 2, 5, 7. And then now you want to basically fill in the DP values once you have this 3.
Wait, DPI is what?
So DP of ij is, suppose that you only have these first 4 values. What is the smallest possible last element of an increasing sequence of size j? So in this case, the smallest possible last element of a size 1 increasing sequence would be 1. The smallest possible last element of a size 2 increasing sequence would be 2. The smallest possible last element of a size 3 would be 5. And size 4 would be 7. And like, it's not possible to make a size 5 So we just set these to be infinity.
Wait, so you have a 2D DP array?
Yes.
So the right column is.
So the right column is what we want to find, and then the left column is what we have already.
Wait, so this is like a 1D array. How does this relate to the 2D DP?
Wait, because this is dp of I when I is at here, and then this is dp of I when I is here.
Wait, so the 5 is DP of.
Yeah,
3,
5.
3.
Yeah, 5 is dp of 3, 3, and then this 3 is dp of 4, 3.
Wait, is J the last? Wait,
J is the size of the increasing sequence.
so the 0 up there is like DP of 3, and that's J or just for J?
Yeah. So this is dp of 3, or I guess, yeah, I can dp of 3, and then this is dp of 4. Okay, so let's say we again have two options, right? We have this 5 here, and this, and we can tack a 3 onto the end of this 5, or we can choose to do this 7, right? But what happens if we tack this 3 onto the end of the 5? The 5 is the last element, right? And we're adding the 3 to the end, which means the 3 is less than the 5, which means this is not an increasing sequence anymore. So in fact, once this array becomes bigger, then no matter what, we're going to have to copy our array over. So this is going to be have to be 7, and these are all going to be infinity again. And so what you can notice about this array is that every single time, we're only changing exactly one element. And you can see over here, every time, we're changing exactly one element. And that element is the smallest element within the array that is bigger than our current element. And so once we fill out the transitions, we can have a simple optimization, which is essentially just every time we use a binary search, we find the smallest element that is bigger than our current element, and then we just replace it with our current element. And so this simple binary search also allows us to find the size of the LIS, which in this case, the answer would just be the size of the DP array, or the largest element within this DP array that isn't infinity. Does that make sense? Okay, now that we have two different solutions for this longest increasing sequence, a subsequence problem, let's move on and talk about some slightly different states and how we might approach solving problems that are slightly more complicated. So, let's say we have a graph and it's directed, or it's undirected and unweighted, and let's say that we want to find a path from node 1 all the way to node n, and it visits every single node exactly once. So, how might we approach this problem? Well, what you can think is, well, let's say we have a Hamiltonian path as shown on the right, then we can define it by the order in which the nodes appear on this path. So in this case, the order would be 1, 8, 7, 5, 6, 4, 3, 2, 9, right? And now, all we need to do is we can just check whether this order is a Hamiltonian path by checking every single pair of these nodes to see, like, for example, from 1 to 8, does there exist this edge? And then for like 8 to 7, does this edge exist? And if all these edges exist, then this is a Hamiltonian path. So one simple solution is iterate over all possible values of this order, right? Which there's n factorial of them, and then just check, does this order make a Hamiltonian path? And so this gives us an n factorial times n solution. But can we do better than this? Remember, in the problem, n is 20. So 20 factorial is approximately like 10 to the 30, which is definitely not fast enough. So how might we speed this up? Well, suppose we wanted to store some intermediate states. What information might we need? So like let's say we're like DFSing, or not exactly DFSing, but just iterating through this tree and creating a path as we go. So we start at node 1, and only node 1 has been visited so far. And we extend our path to node 8. So to visit the next node, for example, to visit node 8, what we want to do is we can just iterate through all the edges of 1 and choose any one of those nodes that isn't already visited. So we need a visit array, and we also need the node that we are currently on. And so, for example, as another example, once we're at node 8, we can check, okay, what are the edges of node 8? It can go to 1, 4, or 7. We can choose one of them, but we can't choose 1 because 1 is already visited. So we can choose like 7, for example, and we can continue the same process where we keep this visited array to make sure that we don't visit a node that we've already visited. So that means that in order to keep this state, we need to store the visited array, and we need to store the node that we're currently on. And so we might have a DP state that looks like, okay, DP of I and this visited array is the number of paths starting at 1, ending at I, which visits exactly every node within this visited array, and not every node not in the visited array. But we run into a problem, right? Because how do we pass a visited array into our DP? Well, one way we can do this is we can represent our visited array as a single integer, as the mask of these bits. So for example, if our visited array looks like 1, 2, 3, and 6 are visited and nothing else is visited, then we see that like it kind of looks like a number in binary. In fact, we write out the number in binary and represent it as a single number to use. So in this case, this visit array would be 78, and a visit array with 1, 5, and 8 visited but nothing else would be like 290, because this is what we do in binary, right? And why might we do this? Like, what are the interesting properties of like representing a visit array this way? Well, if we represent a visit array this way, there are a few things we can do. First, we can manipulate it very easily. If we wanted to set the bit at I, all we need to do is find 2 to the I and just add 2 to the I, right? So let's say mask originally didn't contain I visited. To just set it as visited, we just add 2 to the I to that mask, right? And there's some other really interesting things we can do. So, for example, if we wanted to find the intersection between 2 visited arrays, the nodes that both visited arrays contain, then we can just use the bitwise AND. And to get the union, all we need to do is use the bitwise OR. And so we can also check whether a single element is visited by using this bitwise AND by essentially doing mask bitwise ANDed by 2 to the I. And what this does is, imagine our mask, which is like 1, 1, 0, blah, 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 1, 0, 0, right? And our mask, which is a bunch of zeros, or not, wait, our mask, 2 to the I, which is a bunch of zeros, a single 1, and a bunch of zeros, right? So what happens when we AND them together? Well, when we AND them together, everything outside of this becomes 0. Everything over here becomes 0. And what's over here is whatever is over here in the mask. So using this technique, we can check whether a node is visited. We can set a node to be visited or unvisited, however we want. And we can even check the intersection, the union, or do whatever operations with the bit mask. Yeah?
Wouldn't it be better if instead of doing calculating to the I,
Uh-huh.
you just did some like bit shifty thing? Because like if the I is big, actually calculating to the I might be.
Well, the thing is, calculating to the I in
So
most
we shift on the board.
yeah.
Oh, yeah.
So yeah, calculating to the I in most languages is actually very easy because all you need to do is shift 1 a bunch of times.
Yeah.
So
I say
Um,
do that.
I mean, yeah.
Two star I or something.
Yeah. So normally what you would do is you would do 1 and then you would bit shift it by I bits. Yeah, that's a good catch. Yeah, so how might we apply this back to our original problem? Well, suppose we have a DP, which is, now we can say that DP of I and the mask, which is the number of ways to reach node I, visiting exactly the nodes within mask. Well, what is our base case? Well, let's say we start at node 0, and that means that we've already visited node 0. So that means that DP of 0, 1 would have to be 1, right? And DP of 0 and anything else other than 1 would have to be 0. Okay, so now for each edge going into I, the last edge, or so now to transition, right? What we want to do is we want to figure out what the second to last node is. So we can iterate over the bits in our mask that are set. And that node could maybe have been the last edge. And so we can just add the DP value to our DP while checking whether that edge exists. And so that's essentially what this code is doing. We're iterating over all the edges, checking whether those nodes are okay, and then, or whether those nodes are in the mask, and then adding that DP value. And I guess one final note is that it's actually kind of important that you iterate over mask first, not over the node, because you don't know what order you're going to visit your nodes in. You want to be able to have a well-defined order in which you're able to continue to only visit states that you've already calculated, essentially. And for mask, we know that for any mask that we're going to eventually go to, we're only ever removing bits from it. So if we iterate on mask from small to large, then every mask that we're going to reference within our DP to try to get the answer from is going to already be calculated because we're only ever removing bits from it. So as a small, thing, you should almost always iterate over the mask first rather than over the node first. So with that being said,
Wait, so DP of I mask is a number of Hamiltonian paths using the nodes in mask that end in I?
Yes.
Why do you? Oh, so the problem asks you to put like the number of things that end in
Yeah. Does anyone have any questions?
Do you have to check if A is somewhere we've already visited, or?
So in the code here, we actually don't check if A is already visited. And the reason for this is because we don't need to, because if A wasn't already visited, then when we were at the state A and like mask without 2 to the I, then what we would see is that like that mask doesn't contain A. And so it automatically will just return 0 when it's at that state. So we don't actually need to check whether A is contained within mask. Does that make sense?
Not sure. Oh, I see. Like in the continue.
Yeah. In the continue
Makes sense.
statement, we've already checked whether it's visited or not. So we don't need to check it again. Okay. With that being said, I'll hand it over to Wei Ming to talk a little bit more about different ways we can use Bitmask DP.
Hello. My name is Wei Ming, and then I'll be going over sum over subsets, and so here's the problem statement. You're given an array of length 2 to the n, and the indices go from 0 to 2 to the n minus 1, or exclusive of 2 to the n. And your task is for every mask or integer I from 0 to 2 to the n exclusive, you want to sum a of j, where the bits of j are a subset of the bits of I. So in other words, the bits of j are a subset of the bits of I if for every bit that is on in j, I also has it on. So alternatively, you can think of these integers or masks as corresponding to a set that either contains an element or doesn't contain an element. And you can say that j is a subset of I if the set that corresponds to j is a subset, in fact, of the set that corresponds to I. And you would define these sets in a way that if like a particular bit is on, then that element is in the set. So, and you can see at the example, you can see that 100110 is a subset of 110111, because for all the bits that are on in the first number, notably the first, fourth, and fifth, I guess going from the left, they're also on in 110111. But alternatively, you see that 101001 is not a subset because it has the third bit from the left on, but 110111 does not. Sorry, that was a bit of a mouthful. Those problem statements make sense. I have an example on the next slide, I believe. Cool. Oops. Oh no. Did I put it afterwards? Terrible. Okay, sorry about that. So here, consider the array A, which is equal to 5, 8, 10, 9, 5, 7, 4, 8. You can see like the table mapping the index, and then the index in binary notation, and then to the value. So you see, let's say 0 that has the binary representation of 0, 0, 0 has value 5, or say 4 that has the binary representation of 1, 0, 0 also has value 5. Does this array make sense? So for instance, if you wanted to compute the sum over subsets of the element 5, we'd iterate over, we'd see that 0 is a subset of 5, 1 is a subset of 5, 4 is a subset of 5, and 5 is a subset of 5. And these have values of 5, 8, 5, and 7 respectively, which sum to 25. Yes?
Could you explain again, how did we get 5, 4, 4, and 2? Like value 5 for index 4.
Oh, the array is 0 indexed. So a of 0 is 5, a of 1 is 8.
Oh, I see. Okay.
Yeah.
Thank you.
So with this in mind, we can see that say SOS of 2 would be a of 0 plus a of 2, or 5 plus 10, which is 15. And finally, we have that say SOS of 7 would be 56, or the sum of all the elements in the list. Yeah, sure.
Wait, SOS of X is the sum of numbers in A that are a superset?
Subset.
A subset? So, SOS of an index or a value? Wait, is 2 like a value?
Or two would be an index with a binary representation of 1, 0. 0, 1, 0.
Oh. And this is the sum of values.
Yes, is the sum of values corresponding to the subsets of that index.
Wait. You're saying 5 is a subset of 10?
No. The array elements would be. Wait, so A is an array of size 2 to the n, where say a of I is the element corresponding to the index I, right? So for instance, SOS of 2 would be a of 0 plus a of 2, which would be 5 plus 10.
Wait, so SOS of 2 is the subsets of 10 or 2?
Of 2.
The value 2.
No, the index 2.
So it's subsets of 10.
Oh, okay, sure. Yeah, the subsets of yes, sure. Oh, of 1 0.
Prime is not a subset of 10.
No, subsets of 0, 1, 0.
Yeah, subsets
Not,
of 0
not
1 0.
subsets of 10.
Oh, so 2 is a value.
2 is the
2
index.
is the index, and then 0, 1, 0 is the index in binary, and then 10 is the value.
Oh
I
yes.
think the question is like, how do you define subset of 0, 1, 0?
Oh, sure. Sorry, let me go back a couple of slides. We defined like I guess yeah we defined the subsets of we defined like the subsets of an index I to be like the possible indices J where like J is a subset of I. And a subset means that if a bit is on in J, then it must be on in I as well, but not not necessarily the other way around.
You want to show some examples?
Oh, sure. So, for instance, like suppose we were to consider the number 110. A valid subset, for instance, could be 100 because for this bit which is on, or let's just say this is I. For this bit which is on in J, it is also on in I. But if we were to consider, say, like J is equal to 011, this would not be a subset because for this bit that is on in J, it is not on in I. And then we would say that for a given I, the subsets are all the J that satisfy this criterion. So does this make sense? Sorry, I may have rushed the explanation initially.
Wait, also it's called subsets because like if you treat the ones as like it has this bit, like it's a set where like it has the bits at index 0 and index 1.
I guess it should be 0 and 1.
Yeah. And then so you look at subsets where like it has some of those ones, maybe not all of the ones.
So you can alternatively think of the bit mass as corresponding to sets. And the equivalent of saying that I and J are subsets of each other is equivalent to comparing the set representation as well. So let me rush ahead a little bit. So in that case, do these examples make sense? Yeah. Yeah, so like for instance, again, you have like, say for SS of 5, you have the subsets of 101 would be 110, 001, 000, and 101 as well. Okay, so I'll have the slides out of order. So first we can naively brute force to compute the answer, where for each mask we will iterate over all other masks I and check if I is a subset of mask. We can do this with the bitwise OR operator, which gives us the union of two masks. And the statement if mask or I is equal to mask is saying that the union of the two elements of the two sets is equal to mask. So this would be one such solution. Could someone tell me the complexity? I have went over it. It's like showed up on screen a couple of times, but could someone tell me the complexity and a statement for why it is that? No.
It would be 3 to the n. Because if you say that mask has like I bits. Oh wait. What? Oh wait, it's just 4 to the n.
Yes, it would be 4 to the n because the first for loop iterates over 2 to the n things, and the second for loop also iterates over 2 to the n things. So in total, we will iterate over 2 to the n times 2 to the n equals 4 to the n, different states of, or different pairs of mask and I. So the total complexity of this would be 4 to the n. So our goal is to optimize this would be to optimize this to something preferably much faster. So the next thing we can do is for every mask, we we'll directly iterate over all the submasks of mask. So here I have a piece of code written for how I do that, and I have explanation for how this works in the following few slides. Well, you can see what we do is we initialize I to mask, and we just run a while true, we add a of I to the answer of mask. Then we set I to be I minus 1 and a mask. And also we break when we get to 0. But what we do is we set I to be I minus 1 and mask. So here's an example on the screen where you consider mask, or the highlighted bits are the bits that are on in mask, or the bits that we're trying to iterate over subsets for. Mask is currently 1 0 1 1 1 0 1 1 0, and suppose I was 1 0 0 0 1 0 0 0 0. Then we can directly subtract 1 from I, write that down in binary representation, which is 1 0 0 0 0 1 1 1 1. And finally, we can take the bitwise AND, or the intersection of mask and I minus 1, and this will give us 1 0 0 0 0 0 1 1 0. And you can see that if you only consider the highlighted bits, so between I and I minus 1 and mask, only considering the highlighted bits, you can see that number has also decreased by 1. So if we were to consider the number 1 0 0 1 0 0, and we subtracted 1, we would also end up with this. So like the highlighted bits in I would concatenate together would be this, and the highlighted bits in I minus 1 and mask concatenated would be this. And you can see that if we only consider these bits, we would have successfully decreased the number by 1. And you can see that, and if you were to repeat this process a couple more times, all the way until you get to 0, you'll see that this process does in fact iterate over all the submasks of mask. The reasoning for this is as follows. Let's first think about exactly what it means to subtract 1 in binary. So what we do is, the first step is we find the first one from the left. Wait, I think it should be the right. We find the first one from the right. Sorry about that. And then we set it to 0. Then we set all the zeros to the right of that 1, or before it's been transformed to 0. So we can see that in step 1, we first find the rightmost one. It is underlined there. Then in step 2, we set it to 0. And in step 3, we set all the zeros that were to the right of it to 1. And this is how you would subtract in binary. And does this make sense? Ignoring the mishap about me using the wrong direction for subtraction by 1 in binary. Okay. So if we think about how mask impacts this, we know that all the bits that are not in mask will always stay 0. This is because we initialize it by mask, and at every time we always AND it by mask before continuing. This ensures that we're always dealing with the intersection of some set and mask. So the bits that are not in mask are never on. So what this means that every time we subtract by 1, we'll always pick our rightmost one to be some element that's already inside of the mask. As you can see here in step 1, we ended up picking the third one from the right if we only considered, or the third index from the right, which is inside the highlighted, the third bit from the right if we only consider the highlighted bits. And then in step 3, we subtract by 1, and finally we take the AND of it with mask to reset all the bits that are not in the mask to be 0. And if you see, like, if we were to repeat this process again, we would end up with, say, I minus 1, probably not enough space then. We'd end up with I minus 1 being 1 0 or 1 0 0 0 0 0 1 0 1, and then after we take the AND, it would end up being 1 0 0 0 0 1 0 0, which would again have iterated over, which would again take us to the next smallest subset of mask. Does this make sense? Okay, cool.
Thumbs down, thumbs up.
Yeah, I suppose that's
Thumbs down, thumbs up.
great. So with that in mind, oh yeah, and also it's a bit of a problem, or it's a bit of a hassle to like worry about the case when we accidentally compute when I is equal to 0 at the very bottom here, and we accidentally compute -1 in mask. So we just avoid that by breaking immediately when I is equal to 0. And we know that this is correct because there are no smaller subsets after 0. So this is just a implementation detail. So the final now the question is, what's the complexity of this algorithm? Because it is an improvement, or it's in theory an improvement on 4 to the n, since we're only iterating over masks that are relevant to our bit mask. But how much of an improvement is it? Yes.
It would be 3 to the n.
Why so?
Because if we say that mask has like I1s, then the number of things we need to iterate is going to be 2 to the I, and the number of such masks is going to be n choose I.
Yes.
And when we sum this from I equals 0 to n by binomial theorem, it's just going to be 2 plus 1 to the n, so 3 to the n.
Yes, this is correct. So, one way you can see it is that you are summing n choose k of like, I think it's 2. I don't think it particularly matters. Yeah, n choose k times 2 to the k, which you can also add a 1 to the n minus k here, and this is equal by the binomial theorem to 2 plus 1 to the n. There's a alternate proof which I have written here, which is wait, what? Where did it go? I put the slide in the wrong place. If you consider, like, for a given pair of I and mask, you consider what the bits could possibly be. Like for a given pair of I and mask, and for all like from each bit from 0 to n minus 1, the bit is either not on in mask, so not something we care about, on in mask and not I. So inside the mask, our current I that we're thinking about does not contain that bit, or on in both mask and I. So this means that for every bit, it can correspond to 3 different choices. And as there are n bits in total, this will leave us with 3 to the n. That's a type. Should leave us with 3 to the n possible pairs of mask and I. Another way of saying that, another way of proving that the total complexity of this code is 3 to the n. Or yeah, does this make sense? I guess thumbs up, thumbs down. Cool. So now we're in a bit of a pickle, because even if we iterate over all of the relevant masks, it's still 3 to the n. And the question is, and the question for us now is, can we improve on this? And to improve on this, we'd have to not even be able to iterate over all of the masks. So now let's take a quick detour. Oops, this should not be here. We take a detour to higher dimensional prefix sums. We covered two-dimensional prefix sums on day 2, I believe, in the prefix sum 1 lecture, and we will quickly revisit that. And that higher dimensional prefix sums will actually give us a very important insight towards solving our problem. So here's a piece of code that computes the 2D prefix sum array, writes it into the array P, and it computes the 2D prefix sum array of an array A. And for people who were here on day 2, this is actually different from what we presented then. Notably, you can see that there doesn't really exist a P of I minus 1 or a subtract P of I minus 1 J minus 1 case. But otherwise, this seems like a pretty reasonable thing that could probably solve two-dimensional prefix sums. So I'll go over a couple examples on why exactly this code works, and we can dissect exactly what this code is doing. So suppose A was just an array that had a singular 1 at the index 1, 0. We assume 0 -based because the array is in Python. So initially, we will just set P to be equal to A. So we see that P right now is also an array with a singular 1 at 1, 0. Does it make sense? Like, following? So now let's consider what happens after the second loop. The second set of loops. After the second set of loops, P will end up being an array that only has a 1 at 0, 1 and 0, 2. This is because you can see that the transition that P of ij plus equals P of I minus 1j will happen for the only element that really changes is the bottom left corner, because everything else is just zeros, and we will end up with P as this array. Does this make sense? So now, after you run the third set of arrays, you can see that the ones on each row have all traveled in a sense in parallel, but they've all traveled rightward. And you can see that now P is an array that has ones everywhere except for the first row. And this is exactly the prefix sum array that we would expect for that array A. Does this make sense? Cool. And then we have another example with the 1 initialized at another spot, where initially we see that P is equal to A. Then we see the 1. Then we see that the 1 is sent downward, and finally we see that the 1 is sent to the right. Cool. And here's a little bit of a more complicated example, where we see the prefix, we see the original array being equal to the prefix sum array. Then we see the elements being sent downward again, and we see them sent to the right. Does this make sense? Thumbs up. And so here we have a valid, or here we have a 2D prefix sum code. It's a little bit longer, but it works. Yeah. And we can, in a sense, formalize what's happening here, where after the init block of for loops, the P of xy will just be equal to the sum of A of ij when I is equal to x and j is equal to y, or essentially saying that P is equal to A. Then after, say, the second block, or the for I set of for loops, we will end up with P of xy being the sum of when I is less than or equal to x and j is equal to y of A of ij. And finally, after the for j, or at the very end, you can see that we end up with the actual prefix sum array, where we have I is less than or equal to x and j is less than or equal to y of A of ij. Does this make sense? Great. And here I present like an alternate implementation of of the 2D prefix sum idea. You can see that in a sense, you're iterating over the dimension, and you're adding the contribution. If you're adding the contribution along that dimension, so we can see that I just translated the code into having 2 separate blocks of for loop, to having the first for loop iterate over the dimension, and then the 2 if statements control exactly what we do depending on the dimension. Does this make sense? So these 2 codes do equivalent things, but it's been rewritten in a way that's more scalable on the right. So suppose we wanted to do, like, say, 3-dimensional prefix sums. Then again, we can do something similar. We iterate the dimension from 0 to 3 exclusive, so from 0 to 2. Then we iterate over our prefix sum array. If the dimension is 0, we do the transition on I. If the dimension is 1, we do the transition on j. And if the dimension is 2, we do the transition on k. Does this make sense? And actually, we can see that, let's consider a special case. Suppose every dimension only has size 2. Or alternatively, each dimension has indices that are either 0 or 1. And you can see that, say, for the 3D case, the prefix of 101 would be the sum of A of 00, A of 000, A of 001, A of 100, A of 101. Or the prefix sum of 110 would be A of 00 plus 010 plus 100 plus 110. And you can see that these states, or these definitions of prefix sums, are very familiar. In fact, they're identical to the SOS. They're identical to what the SOS function or array will compute. We can see that the three-dimensional case where all the dimensions have size 2 is exactly equivalent to computing SOS over an array of size 2 to the 3. Does this make sense? And I can go back to the slide in a moment. I think the next slide is a little bit more helpful. And we can see, and the reason this is true is, suppose S and T are both bit masks over the bits 0 to n minus 1, then we can say that S is a subset of T if S of I, or the Boolean denoted, or like 0 when S contains, or 0 when S doesn't contain I, and 1 when S contains I, is less than or equal to T of I for all I. So this makes, it makes sense that SOS is actually equivalent to finding the prefix sum array over an n-dimensional space where all the dimensions have size 2. Does this make sense? So here we have an example again, back to our favorite array from earlier. And we can see with the first dimension transition, we're taking, we're considering the rightmost bit or the smallest bit, and we say the transition would have us go from, will have us increase 0, 0, 1 by 0, 0, 0. So we go from, so we add 5, we add 5 from 0 to 1. Or alternatively, we add 10 from 2 to 3, and we add 5 from 4 to 5, and we add 4 from 6 to 7. Does this make sense? In a sense, if we were to write out a three-dimensional prefix, the three-dimensional prefix sum, and execute exactly what the for loop does, you can see that what we're doing here right now in the first dimension transition is we're taking all the states that have the last bit being greater than 0 or equal to 1, and adding exactly what that state would be if that last bit was 0 to it. So for instance, we'd add 1102, 111. Yeah, we'd add 6 to 7. Does this make sense? So here I simplified the sums. Then if we consider the second dimension transitions, we'll be doing the same thing but for the second bit, where we'd add the value of 0 to, so we'd add the value of 0 to the value of 2, because the second bit corresponds, the second bit, or if we were to remove the second bit from 101, from 010, we'd end up with 000. So we'd now set the value of 2 to be 10 plus 5 is equal to 15. Or we'd set the new value of 3 to be 19 plus 13, and so on and so forth. And we do all the transitions, and the values that we change are exactly the values that have the second bit on. Does this make sense? And then finally, we do the same thing for the third dimension, which would be we change all the elements that have the third bit on, which would be 4, 5, 6, 7, and we add 0, 1, 2, 3 respectively to them. Yeah. And you can see that here we end up with our final SOS array, which we can check a few values to see that they're correct. Like for instance, the SOS of 7 is in fact still 56, or the SOS of 2 is still 15. And the SOS of 5 is still 25. And here's just that in a table form. And I think it's beneficial to think about try to track the transitions for a specific final value. So if we're to think about what we want to see SOS of 5, we expect it to be 25, and it will be 25 if we add the values of 0, 1, 4, and 5 to SOS of 5 at some point. So what we can do is try to imagine this DP transition. Try to imagine this transition as you go over dimensions, and see exactly when these what these values do before they eventually make it to the answer of 5. So what we can see is that after the first transition, the values of 0 and 1 will both get collapsed together into 13, into the new value of 1, which would be 13. So 5 plus 8 equals 13. And we see that the values of 4 and 5 combine together to join at 12. And then after the second transition, nothing happens. because 5 does not have the second bit on. And finally, after the third transition, we'll add 13 and 12 together to get 25. Does this make sense? Great. In that case, we can again try to rewrite the code. And what we can see here is by collapsing our DP states into a bit mask, the code actually becomes very clean. Where the code on the left is our previous code for 3D prefix sums, and our code on the right, we first iterate the dimension until 3, then we iterate over all the masks, and then for each mask we check if we only consider the dimension, the dimth bit of that mask, we check if that is on. We do that by mask and t to the power of dim is greater than 0. And finally, if it is on, then we add then we do the transition where p of mask plus equals p of mask minus 2 to the dim. So this would be equivalent of, for instance, if we were to look at, like, suppose like dim is equal to 1, and we were to look at the bit mask 110, we would check that this bit, where 2 to the 1 is in fact on, and then we add the value of 110 minus 2 to the 1, which is equal to 100 to this, to the value of 5, or to the value of 6, which would be equivalent to adding the prefix, adding the value of 4, adding the prefix sum value of 4 to the prefix sum value of 6. So does this make sense? And actually, you can see that now. There's no reason why we should choose 3 specifically. We could actually. Here we can. Here we can see that the if statements correspond. The if statements on the left side correspond to this if statement here on the right, and the transitions on the left correspond to the singular transition on the right. And we can see that there's actually no need for us to limit ourselves to 3 to the n. This would, or 2 to the power of 3. This code would work with 3 substituted for any n. And we'd end up with a final complexity for computing the sum over subsets, a final complexity of n times 2 to the n, which is a significant improvement from 3 to the n. And additionally, our code is also quite short. If we were to erase the comments, it would effectively be 8 lines of code to compute the sum over subsets array. Yeah, and